Ah, okay. Thank you. But here the important idea is that you make use of the environment. But it still remains very challenging. Now, another technique which has been also very successful experimentally is to engineer your environment in order to engineer the dissipation processes that you want to, for instance, reach a steady state which is an entangled state. And this has been done, for instance, with superconducting circuits or with trapped ions, and it was really successful. So, for instance, in this experiment with superconducting circuits, they need 6 external drives, and they use some measurement and feedback that is realized via those elements to drive the quantum system into the singlet state. But this requires lots of external control and engineering. So the question that I want to ask in this talk is whether we can come back to simpler setups, in other words, to make use of out-of-equilibrium situations and see if this is enough to generate some quantum states interesting for quantum information processing. The answer is yes, and there have been already many works. So it's possible to generate entangled state in the steady state regime, just making use of out-of-equilibrium environments. So this has been done with several, this has been proposed, with several quantum systems. For instance, atoms coupled to cavities that are driven by an incoherent light, and then the 2 cavities become entangled. Or qubits that become entangled thanks to a noisy channel to which they are both coupled. Or also, there have been, or people have proposed to entangle mechanical oscillators. So here, the idea or the principle behind those protocols is the following, that you have some external environments that you do not control. There is some incoherent couplings to the quantum system, but between the quantum system, you engineer a specific Hamiltonian. For instance, an Hamiltonian of the Ising type or of the XX type, or a flip-flop Hamiltonian. But of course, you have to have some specific interaction between your quantum systems to reach the entangled state that you want. So let me give you a very simple example. That's a quantum summon machine that we proposed with my colleagues in Geneva. And here you have 2 qubits. So qubits are 2-level systems, and they are each coupled to a bath at a different temperature, so cold one and hot one. So there is a heat current that flows through the 2 qubits, okay? And in fact, we have shown that by implementing engineering flip-flop interaction, so I will show you explicitly what it is, the heat current is then sufficient to generate entanglement between those qubits, which were initially in a product state. So how do we characterize entanglement? Is by looking at the concurrence. The concurrence is a monotone measure for entanglement, and you just have to remember that it takes the value 0 for quantum systems in a separable state or in a product state, and it takes value 1 for maximally entangled states or Bell states. So you see that when there is, as soon as there is a temperature gradient, this is the concurrence as a function of the hot temperature for 2 values of the cold temperature. So what is important is that as soon as you have a temperature gradient, you generate some entanglement. Concurrence is not equal to 0. But I will come back to this later. You see that here, okay, the concurrence is finite, but remains very small compared to 1. Okay, so you generate some entanglement, but it is weak. But this is done using only incoherent couplings to thermal baths without any external control. So let me explain you a bit more in details how this machine works. So this is my quantum summel machine. Here is a flip-flop Hamiltonian I mentioned before. So you see this labels the quantum state, so the ground state and the excited state for each qubit, 0 and 1. And you flip so the state 0, 1 to 1, 0. Okay, this is clear for everyone? So once you have this interaction Hamiltonian, you couple your qubits to a thermal bath at a different temperature. The thermal bath can be characterized by, the thermal bath is characterized by its temperature. What is important is that these qubits are energy degenerated, okay? So, and you have some time-independent interaction Hamiltonian. So when you start looking at thermodynamics, this implies that there is no work in your system, and there is only heat exchange in this system. And this is how you can characterize autonomous quantum thermal machines.
What is work there?
What is?
Work.
So work you can define it from when you have some time dependence in your Hamiltonian. So it's one form, if you want, of the that the energy can take within a physical system. You have the first law of thermodynamics, that a change of energy takes either the form of work or heat, and heat is characterized as an incoherent form of energy. So it only depends on the change in the population of your system, whereas work depends on a change in time of your Hamiltonian. Yeah. Well, yeah, the energy levels that change in time. What we have done to investigate the dynamics of this machine is to look at the reset master equation. Here, in simple words, this reset master equation is just a probabilistic equations for the dynamics that says the following thing. So the time evolution of your density operator rho for your 2 qubits, so that's the reduced density operator, has a free evolution given by this term. And then your qubit, at each instant of time, it will have a finite probability, P, here, that its state is reset to a thermal state set by the temperature of the bath to which it is coupled. Okay, so this is the only thing that the reset master equation says. So you see, for instance, if we take the cold qubit, so the qubit coupled to the cold bath, that's the finite probability that the density operator is reset to a thermal state defined by the temperature of the cold bath, where you see that then you replace the state of this qubit by the thermal state, you do the tensor product with the partial trace of the density operator that describes your right qubit, and this is just the difference in your density operator. So you just have to remember that it's a probabilistic way to describe the coupling to your environment. It is important just to link this master equation to well-known master equation that takes the Lindblad form. In fact, you can show that this master equation is equivalent to a local Lindbladian master equation plus some additional dephasing. But why do we use this one? It's because it enables analytical calculations which are quite elegant. But then it will mean that you can also match this to a physical implementation of the machine. So now, from this reset master equation, so here I just show you what we compute, okay? But then I will show you some plots and why, what's the physics that takes place in those systems. So that's the master equation. From this reset master equation, you can compute the steady state, okay, of your 2 qubits. From the steady state, we compute the heat flow. So the heat flow depends on the probability, for instance, the heat flow to the cold bath. So it depends on the coupling probability to the cold bath, on the energy of your system, and on the population on the excited state. Okay, it's very simple. Then from this steady state, I can compute the concurrence, which is so the measures that can be calculated from the eigenvalues of this matrix. So this is a very well-known tool in quantum information. And this is what we get. So for the heat flow, so again, that's the heat flow and the concurrence as a function of the temperature of the hot bath, and for two values of the cold bath. So let us look at the blue curve first. You see that so the temperature of the cold bath is 0. So as soon as I have a temperature gradient, as TH is finite, I have some heat flow, which I expect, okay? And I also have a finite concurrence. When I go to a warmer, cold temperature, so Tc, for instance, over E is equal to 0.2, I don't generate straight away a heat current. I have to get again this temperature gradient. And then again, when I have a heat current, I generate some entanglement. So this is one of the simplest quantum thermal machines that is able to generate entangled states. So now, interestingly, because it's a very simple scheme, you see, that works autonomously, it has triggered interest among experimentalists. And so now we have established a collaboration with a group of Benjamin Huard in Lyon, who is an expert in manipulating superconducting circuits, and he's realizing with his group this quantum thermal machine. So here is just a picture of the sample, and here, so that's, well, I don't know exactly how they call this, but like a numerical drawing of the sample. And here are also the two quantum systems. These are transmon circuits, and these are the transmission lines. And in fact, how the main achievement was to propose an experimental implementation of the environments. And so this can be done when you realize that these transmission lines, so there is a current flowing through these transmission lines, and this current will fluctuate. And in fact, the spectral density of the current noise so depends on the energy of your quantum system, depends on the admittance of your circuit, which is related to the impedance, and depends on this distribution, well, on this function, which depends on temperature. So you see that by controlling this noise, you can in fact implement an environment with a hotter or colder temperature. And this is what they do. So so it's an ongoing experiment, okay, it's not completely working yet, but this will be a proof of principle of an autonomous quantum thermal machine that is able to generate entanglement. So, but there is, okay, now if we want to go further, there is a little drawback, is the fact that, as I told you, the amount of entanglement that you produce is rather weak. And why is this a problem? It's because if you want quantum states that are useful for quantum information processing, you need strong entanglement. And what does strong mean? It means that, for instance, you can violate Bell-type inequalities. And why can this, for instance, be useful for? It's, maybe you have heard about this, about device-independent theories, where you would like to trust, well, you don't need to know anything about your measurement apparatus. You just want to investigate the statistics at the output of your experiment, and from this certify that you have an entangled state. So this is the idea of device-independent theories, and for this you need states that violate Bell-type inequalities. So, and for sure, this kind of states cannot do that. So, with my colleagues in Geneva, we came up with a more advanced thermal machine, which is the following. Do you have questions on the first part?
You are saying that there are degrees of entanglement.
Yeah, you have different strengths of quantum correlations. And for instance, this you may have heard of. So you have states that are entangled, but are not non-local. There is this idea of non-locality in the degree of quantum correlations, and non-local quantum states are the highest or the strongest quantum correlated states, if you want. Yes?
I didn't quite understood how you implement the interaction with the bath, both theoretically and experimentally.
How you can implement the environments experimentally?
Yeah.
That's your question?
Yeah.
Well, in fact, the main idea is that you have some John Nyquist noise in your that will affect your quantum circuit, and you can relate this noise, so it has a spectral density, and this density can be related to a temperature. So, if, in fact, by controlling the noise, you set some temperature to your environment.
Is that some kind of semi-classical model?
No, because here you can. Well, you have some. I know that you can write some operator for the current. In the transmission lines, and so you compute the noise, and so I think it's no, it's not semi-classics. You really quantize everything. Yes. Yes. Yeah.
Is there a guideline on how the difference of temperatures of the baths have to be in order to get a maximum of entanglement?
Yeah, so in the plots that I showed you, we have optimized over various parameters, and the curve I showed you is the one with everything optimal in the coupling strengths and as a function of temperature, okay? So, but there is not much to do. But in the next machine that I will show you, we see that theoretically we can find some optimal temperature gradient, and experimentally we have something else, but yes, there is some range of temperature. But surprisingly, this range of temperature is rather large, in fact. It's not so critical. Yes?
So continuing with the previous question, so you have explained how to generate the bath somehow, but now the interaction between bath and qubit or between qubits, so you...
Okay. Yeah, it's good. So good question. Here's a flip-flop interaction Hamiltonian between two qubits. Can be implemented in a relatively simple manner with it's called a direct inductive coupling. So in fact, in all these superconducting circuits, they have, well, with the quantization of the Hamiltonian, the energies, the different variables, in fact, they have derived some interaction Hamiltons that are possible, and with a direct inductive coupling, this gives you exactly the interaction you need.
Do you need some kind of active control to implement them?
So, yeah. But why it is called an autonomous machine? It's because you have to engineer this interaction Hamiltonian, but once it's done, no? You turn it on, this interaction Hamiltonian, and then you couple your qubits to environments and you let the machine run, and there is no other control on it.
So
Yeah.
when you say turning on, you mean you are like sending some?
Yeah, it's some with external lines, external fields that turn on this direct inductive interaction.
But doesn't then it look more like you are this signal that you are sending some kind of the work you are doing in the system? So you are sending some energy and you have to bath,
yeah, okay, that's a good point. In fact, when you, when you, I think there are two levels. When you turn on this inductive coupling, this is done technically, but okay, I don't know exactly how. But then once this coupling, well, this coupling is turned on, in fact, your Hamiltonian does not depend on time, and it's just this flip-flop term. So in that sense, I think it's correct from a thermodynamical point of view to say that there is no work. But then, okay, it depends on the size of your open quantum systems that you consider, no? It's, we also produce some works, no, by manipulating. No, but I think it depends on the size of the system you look at. Okay, so now let me go to the more advanced thermal machine. So let me just repeat that the goal now is to generate stronger entanglement. And how do we do that? In fact, we have increased the size of the quantum systems which are the core of the machine. So instead of qubits, we are now working with qutrits, which are three-level systems, labeled 0, 1, 2. We consider, again, a specific interaction Hamiltonian, which is the following one. And very simply, this Hamiltonian generates, so again, flip-flop interaction, but between all possible transitions, okay, between the transition 0, 2, 0, 1, and 1, 2. Now, again, I want this to be embedded in a thermal machine. So I couple one of the qutrit to a hot bath, again via this incoherent coupling. I couple the other one to the cold bath, and I can again write a reset master equation, calculate analytically the steady state solution, and here, if I don't do anything else, as before, I get a steady state that is a weakly entangled state. Okay, there is no magic. It's increasing the size is not enough to generate strong entanglement, but I still generate entanglement in an autonomous way. And now, in fact, to generate strong entanglement, we will use some filtering step that we add, and that will allows us to announce whether we have an entanglement or not. So how does this work? So this is the machine, and the filtering step consists in post-selecting the two qutrits and to project the two qutrits onto a 2-qubit subspace. So I select the two lower levels of the hot qutrit and the two upper levels of the cold qutrit. How can this be done? This can be, so theoretically, it's by considering a projector onto the lowest two levels of qutrit A and the upper two levels of qutrit B. And experimentally, but we can discuss that in more details, you will have to make kind of projective measurements of the upper level of this qutrit and the lowest level of this qutrit. And if these two states are occupied or unoccupied, you can know whether you are in this subspace or not. So what does happen now? If it fails, meaning that your qutrit are in level 2 of the red one or level 0 of the blue one. So this was, you could detect some population. Then you are in this subspace, and in fact you can show that you have a product state. So your entanglement generation procedure has failed. However, if this step is passing, so that nothing is in 2 and nothing is in 0, then you can show that you have entanglement. And moreover, it's possible to show in a certain limit that you have a singlet state, so a Bell state, a maximally entangled state. So let me detail a bit. So yeah, okay, just this is why we call this heralded strong entanglement, because we know that if this filtering step was successful, then we have strong entanglement, okay? Why does it work? So let me, okay, maybe just mention that here we have the singlet state in the limit where TA is infinite and TB is equal to 0, okay? So we have the maximal gradient. And in this limit, interestingly, we can compute the analytical solution, and we can show that we have a singlet state. In this limit, you see if TA is infinite, you have a thermal state for the hot qutrit, meaning that you have probability 1/3 to be in the 3 levels. If you have the cold temperature being equal to 0, each time you reset, you will be reset to the ground state. And so the interaction Hamiltonian that we are considering, you see it will take some excitation in the ground state and bring them in the subspace where we generate entanglement. And when you reset to the ground state the next time, in fact, you don't destroy the coherences that you have created in this subspace. So that's a bit the trick behind this interaction Hamiltonian. You can also see that because if you just consider the first two terms and compute the commutator, in fact, you see that your unitary evolution will generate some coherences in the subspace, in the 2-qubit subspace that we are interested in. So this is why we can generate entanglement. Okay, but of course you have to pay a price, no? Because this filtering procedure, it's a probabilistic way to enhance the amount of entanglement that you create. And so what does it mean? It means that here, okay, P success is my success probability of being in my 2-qubit subspace where I generate strong entanglement. And this is the negativity, which is a measure for entanglement. You just have to know that negativity 0.5 corresponds to a singlet state, to a maximally entangled state, negativity 0 to a product state. So you see that you can generate singlet, but okay, with a success probability close to 0. However, you have a finite, where is the point? You have a finite negativity up to, with a success probability of 25%. And I told you that this machine can generate states that can violate Bell-type inequalities. So to show this, we have looked at the CHSH inequality, which is a Bell-type inequality. This value is plotted is shown as at the red dotted line. And what is important is that if this value is below 2, then you have you don't violate this inequality. If it's above, you violate it, meaning that you have some non-local quantum state and very strongly entangled states. And you see that you violate this inequality with a probability up to 12%. So you have to pay a price, but using only thermal resources, you can generate states that violate Bell-type inequalities, which in general is not an easy task to do. Okay, so this is what I just explained. So now, again, we have proposed some experimental implementations of this machine. Here, I don't want to go into details, but this will be what the Lindblad master equation would look like for our machine. We took some realistic values from latest experiments, And we computed so the negativity, that the density plot of the negativity as a function of the cold and the hot temperature. And what is important is that we showed that we could violate Bell-type inequalities up to a success probability of 5% when we include dephasing and so on that may arise, that will arise in an experiment. Okay, so so now, okay, what is amazing is that with this machine, you can also generalize these ideas of heralding entanglement. And in particular, you can generalize it in order to get singlet in arbitrary dimensions. So the idea is the same. Instead of working with two qutrit, you work with qudit, so in arbitrary dimension d. Okay, so these are quantum systems with d levels. You couple each of them to a cold bath and a hot bath. Then you post-select on the lower, well, on the d-1 subspace. And in those subspace, when the projection is successful, you will generate so singlet state in d-1 dimension. What we are currently doing is also, so you see you have two types of generalization, no? Either you stay with two quantum systems, but you go to arbitrary dimension in those quantum systems, or you stay with qutrits or qubits, but you consider n copies of these quantum systems. And so if you consider, for instance, another qutrit which will be coupled to a cold bath, in fact, again, you can compute the steady state. You will have some weak entanglement, but when you do the projection onto a specific subspace, you can show that you can generate a GHZ state. And let me mention that this GHZ state is a very specific quantum state for quantum information, and it may allow, well, it has some application for quantum metrology, and in general, it's very challenging to produce it, okay, even with lots of control. So I'm not claiming that this is the best way to do it, but I'm just saying that this is, well, paves the road to a new way to use the environments with not so many control to realize quantum states for quantum information processing. So, okay, that's the summary of what I told you. So I presented you some examples of autonomous quantum thermal machines, and the main idea that you can, well, with just incoherent couplings to thermal baths, you can generate, in fact, entangled states which are non-trivial and that can be useful for quantum information processing. If you want strong entanglement, we found a way with this filtering step. Interestingly, this has led to experimental collaborations, so I hope that this will motivate new works. And okay, there are many possible outlooks. For instance, can we generate cluster states, which is another type of quantum state very interesting for quantum information processing? Or can we look, for instance, at state-of-the-art experiments, for instance, with superconducting qubits, they have realized a loop of 10 qubits or qutrits. And so what is the kind of quantum states that we could generate using thermal resources? And I'm also specifically interested also in developing new witnesses for certifying the presence of entanglement, which are based only on thermodynamical properties. So right now, witnesses are, well, for instance, to certify quantum correlation, you typically do the tomography of your quantum state. And, but maybe by measuring heat or heat current fluctuations, you could access also this. And so, yeah, so these are a bit my motivations. I thank you for your attention.